my idea is to summarize here the angular redshift fluctuations. This is a new observable that I've been working on for quite some time now, for a few years, even though most of the publications came out in the last 2 years or so. So now, finally, after a long effort, the 3 of them have been published, have been accepted, and they're, they'll probably be published, 2 of them next week because they are letters. And so this is about, this talk is about angular redshift fluctuations, which is something related to the standard 2D or angular clustering. So so this is, thank you. So this is, let me just focus here on in this bottom right equation. This is standard 2D clustering. Let's assume that we have, like a spectroscopic galaxy survey where we have redshifts for each of the galaxies. Then, what we propose doing here is some type of tomography, right? So we pick up some central redshift, C-OBS, and then we pick up a Gaussian centered upon this central redshift with a given width. And then we can do 2 things here. We can do standard 2D clustering. That is, we assign to all galaxies a given Gaussian weight, which is just given by the distance of the given galaxy towards the central redshift upon which the Gaussian cell is centered. And then we can do just this simply 2D clustering, which is just how many galaxies we have in every pixel, given after assigning each galaxy this Gaussian weight, and then we divide by the angular average of these weights over all pixels on the footprint. This is the standard 2D clustering. This is just the density contrast of galaxies, angular density contrast. And here, one could do a different thing, which is what we call angular redshift fluctuations. So these would be angular density fluctuations, and this would be angular redshift fluctuations, which is the same thing, but the weight is modified by the difference between the redshift of that given galaxy and the average redshift of all galaxies, inside the shell, right? Which is the average, the average redshift of all galaxies close to this central redshift. And we could compute angular redshift fluctuations as this thing, right? As just the sum weighted over the average weight throughout the full footprint. Here I'm assuming that the observed redshift is given by the Hubble drift, by the Hubble redshift, Hubble flow, plus some peculiar velocity redshift, which is where most of the cosmological information is coming from. So for you just to train your eye, my question to you is, this is a map of angular redshift fluctuations when you consider both the Hubble redshift and the peculiar velocity redshift. And this is what you see when you just we just drop the Hubble redshift. Do you see, this is for a given galaxy survey at redshift 0.3. This is a simulation, a numerical simulation. My question to you is whether you see any similarity between the 2 maps. We can do it in a different simulation, like this one. Again, this is angular redshift fluctuations. These are just the projected velocities under the Gaussian shell. Do you see a similarity between the 2 maps? There should be indeed some similarity between the 2 maps. And this is how this project was born. I was computing, the correlation coefficient, which is just the product of the angular redshift fluctuations times the velocity, the peculiar velocity redshift, over the square root of the square of the amplitudes. And you see that, these 2 signals, the peculiar velocity redshift and the angular redshift fluctuations, for different shell widths are correlated at there's a range of scales depending on central redshift and the width of the Gaussian shells, but they are at the level between 50 and 70% or 80% correlation, right? So indeed, what are these things? What is this observable sensitive to? So both the 2D observables, the angular density fluctuations and the angular redshift fluctuations, they are sensitive to a slightly different combination of cosmological parameters than what you are sensitive to when you look at 3D clustering. When you compute when you handle angular observables, then you're sensitive to the peculiar velocity redshift, which is given by this equation, right? So essentially it's F, which is the logarithmic growth rate of the structure. Then you have this function E of C, which is the normalized Hubble parameter. And then you have you're sensitive to the density, right? This is for the peculiar velocity redshift. However, when you project redshifts into distances, then you're taking the peculiar velocity redshift and you multiply by this function, which is just the Hubble function, the inverse of the Hubble function. And in this way, you kill this dependence, right? So when we say that when people look at redshift space distortions in large-scale structure surveys, they are typically sensitive to F sigma 8. Here, however, if you're handling angular quantities, then you are sensitive to EF sigma 8. Sigma 8 is just the amplitude of the density perturbations. So probably, sorry, maybe this was a bit too specialized, and I haven't properly introduced what is F sigmoid. But yeah, I hope people follow me on this. Anyway, so so what we did is we tried to understand what is this new observable, and we just wrote a linear theory, right? Under the assumption that linear theory applies and that perturbations are small. So if you do this, then you find out that these angular redshift fluctuations are actually sensitive to the density field under the Gaussian shell, for a given central redshift and a given width. Then this angular redshift fluctuation is sensitive to the density and the line of sight velocities. So here I have written some equations. This is the functional f of function y, which is just simply the integral of y along the line of sight, weighted by the average number density of tracers of galaxies, and weighted by the Gaussian weight, with a given width, right, and a given central redshift. So in reality, what we're showing here is that the angular redshift fluctuations is just these two functionals of something that is related to the density of matter or the density of galaxies. But there's like a term here, which is giving you like a gradient or a dipolar character. Like this is telling us that these angular redshift fluctuations are sensitive to the gradient, to the redshift gradient, to the variation under the Gaussian shell of the density field. And same for the velocities. If you ignore the contribution to the observed redshift from gravitational potential terms that are usually negligible, then this functional is telling you that the angular redshift fluctuations are sensitive to the radial variation of peculiar velocities under the Gaussian shell. Okay. So from these expressions you can compute under linear theory the angular power spectrum, right? So if we have like this field, we can decompose it on the sphere, compute the correlation function, which is just the average of the product of this quantity along two directions that are different by an angle theta, and from this you can compute the inverse Fourier transform of this, which is the angular power spectrum. And we have provided or found expressions for this angular power spectrum. This I should have said. The thing is that because of these finite weighting functions, the angular redshift fluctuations carry additional information on top of that on 2D clustering, angular density fluctuations. This is shown here in a paper that was finally accepted, which is telling you how angular density fluctuations and angular redshift fluctuations carry information about some cosmological parameters like the linear bias or the FNR, which is an inflation-related parameter that is conditioning the amplitude of the CLs at large angular scales, of the CLs on large angular scales. So you see that if you do some Fisher matrix analysis, when you combine both ADF and ARF, you shrink the error ellipses, right? So this is the sensitivity to the peculiar velocities. This is the sensitivity to the linear bias. This is sensitivity to a different cosmological parameter that is compromising, that influences the amplitude of the CLs. So when what these ellipses are showing is that they shrink, these error ellipses shrink when you combine the two observables. Okay, mostly because ADF and ARF, the two observables, angular redshift fluctuations and 2D clustering, are orthogonal, right? They do not overlap to each other. Anyway, so this, so we're computing the linear theory prediction for this, and then we're checking, we're, under I'm being conscious that these observables are mostly sensitive to these two combination of cosmological parameters. B sigmoid is telling you the amplitude of the density perturbations versus redshift, and F sigmoid is telling you the amplitude of the line of sight peculiar velocity. These are the two cosmological parameters that one is sensitive to with ADF and ARF. And this is telling you for a given central redshift of 1.3 and a width of 0.01, you see what is the relative contribution. So in black is the total. Then you have, when you compute the angular power spectrum, as you have shown this, you have like a density term coming from here. You have a velocity term coming from here, and you have twice a cross term that is linear with the velocity of with the galaxy bias. This dg is simply the velocity, is the bias relating the matter clustering and the galaxy clustering. Right? You have usually galaxies are biased tracers of matter, and we are assuming that this biasing scheme is sufficiently well described by a simple constant, a simple bias factor here. So so as you see, the density term, which is the blue one, dominates on the small scales or large multiples, large multiple L's or small angular scales. Then you have the green time, which is the cross term, velocity density twice. And then you have the you have the velocity term, which has more contribution on the larger scales. So the contribution of velocities is dominant on the larger scales, at least on larger scales or smaller multiples than density, as one would expect. Then we compare our theoretical expectations with this output of 100 Coulomb-Mach for this central redshift for the Gaussian shell and its width. And what I'm showing here are results in real and in redshift space. So the dashed line is the theoretical prediction. The dot line is just below by 5%. And here is the relative error, right? So you see that if you do things in real space and you disconnect the peculiar velocities, then we get very good agreement, right? Around 1% or so, which is what you would expect from 100 Coulomb-Mach, okay? However, up to relatively high multiples, small angular scales. But when you consider the velocities in redshift space, there seems to be like a persistent 5% or so error here, which is due to nonlinear velocities. So you have to assume that your matter particles are kind of thermalized, Gaussian, like a thermal, if they had like some extra random velocity. And once you include this, then you find much better agreement with the output of numerical simulations here, both for the angular density fluctuations and the angular redshift fluctuations. So this linear theory prescription is working more or less fine, at least with our matter particles in this Coulomb-Mach. These Coulomb-Mach were built on a succession of an ensemble of 100 boxes of, I think, 1 gigaparsec on a side or 3 gigaparsec on a side. Okay. So and then this is this plug went to the paper. The important thing is that you can also compare to the Millennium XXL, which is the bottom panel here. It is just one single simulation, and again, red is when you consider the velocities in redshift space. Black is if you switch off velocities in real space, and on the full lines and the solid lines are the theoretical predictions. The important thing here is that there is a correlation between the velocities, the line of sight velocities, and the angular redshift fluctuations. And this is the correlation coefficient. The theoretical expectation is given by the solid line. The recovery from the simulations is given by these circles, these red circles, which are almost look like a line. And it's very good. And it's close to 1 for a wide range of angular scales. Okay. Also, the correlation between the angular redshift fluctuations and the angular density fluctuations is very small. It's compatible with 0, as you see here. Okay. So ADF and ARF are uncorrelated for narrow shells, but angular redshift fluctuations are highly correlated to line of sight velocities. This is what I want to emphasize. This is one. Since I'm afraid I'm running a bit, let me see what time is it. Well, it's fine. So then the thing is that the angular redshift fluctuations compute the average redshift of galaxies in a given pixel. Regardless, we're missing some galaxies in that pixel. So if you assume that there are in observation some systematics, either additive or multiplicative given by gamma or additive given by the product of gamma times epsilon, that are biasing your observed number of sources of galaxies. These systematics, when you compute angular redshift fluctuations, because the way we're computing the angular redshift fluctuation, which is just simply the average redshift of galaxies in a given pixel, we don't care so much. We don't care at all where we're missing like 20, 50, or 30% of the sources, because what we care about is about the central, the average redshift of that galaxy, of those galaxies that are falling into a given pixel. This means that you are insensitive to most of the systematics. If you actually work out the algebra, you find out that the observed angular redshift fluctuation field, you cancel out. You're totally insensitive to the multiplicative bias, and then this additive bias, if it's constant under the Gaussian shell, under the redshift shell, which are typically pretty narrow, we pick them to be like of a width of 0.01 or 0.2. If your systematics, which could be due to sky, to the sky brightness, or to the moonlight, or to the density of stars, or extinction, these things usually do not depend on redshift. So if this epsilon pulls out of the integral, then this thing cancels too, and at the end you are not affected at all by systematics, right? So of course there might be some systematics, but our experience is that angular redshift fluctuations is a robust observable in the sense that it's little affected by systematics that you typically bias the number density of objects the number of galaxies that you observe. Let me move on. So let me show some application on real data. So we're applying this. Oh, hit point year 13. I think it's year 12, by the way, but now I'm not sure anymore. So the paper got accepted, and we're writing year 12. Actually, it might be wrong. It might be year 13. Never mind. So we're applying this angular redshift fluctuation study on this on the most large luminous red galaxy samples for low C, which is low redshift, given here, or for the C mass sample, which is slightly higher redshift from 0.4 up to 0.8 or so, right? So this is the footprint of the, which is about 10,000 square degrees. And this is what we get when we apply our formalism on a set of 300 MOCs. And the multi-dark-patchy MOCs are simply galaxy MOCs built from numerical simulations that resemble the real BOSS data. So the first thing we did is, okay, we have a machinery that computes the angular density fluctuations and the angular redshift fluctuations. And then we try to measure both parameters, B sigma 8, which is just the bias, and EF sigma 8, which is telling you the amplitude of peculiar velocities. This plot is showing the ratio of the obtained values over the fiducial values. So for velocities in a standard lambda CDM cosmology compatible to Planck observations, we see that the average of these 300 MOCs, we are recovering an amplitude of the velocities. That is what you would expect from the lambda CDM prediction. Okay, you have different symbols here because we are ignoring all information, all scales that are non-linear, that are below 50 megaparsecs, 60 megaparsecs, or 70 megaparsecs. And you see that there is little dependence on which scale we pick up, as long as it's about 50 megaparsecs. This is a very simple model. There is no linear, there is no modeling of the tidal tensor. There is just one single bias parameter, linear bias parameter. There is nothing else. This is extremely simple thing. And here in red, I'm showing the recovered value for the bias, right? And it's close to 2. And it has tiny error bars, as you can see, right? So we have like 5% precision on B sigma 8 per redshift beam, and an overall 77% precision on EF sigma 8 through the entire redshift range. Anyway, so we picked up 32 redshift beams from redshift 0.26 to 72.72, which is pretty much the redshift range probed by the low C and C mass galaxy samples. And we consider in each of these central redshifts three Gaussian shots of varying width. And we were computing ADF and ARF for every central redshift and for every width. So this is for you what the data looks like. This is a central redshift of 0.62 and a narrow shell of 0.01. And you see that the minimum for the density contrast, you have typically very small values of -1 when you have almost empty pixels, and you have huge overdensities of around 6 or 7 when you have like clusters or superclusters or really dense regions. However, the angular redshift fluctuations are way more linear, right? You see? So they are like -3 sigma plus 4 sigma here. They are, so we are expecting something like centered upon 0 and the typical width of, sigma C of 0.01, right? So we have some excursions as -3 sigma, some positive excursion in this particular pixel here in the frontier, in the edge of the mask at 4 sigma. But all the rest, the histograms are really normal, are really Gaussian. This is a way more Gaussian statistic than the angular density fluctuations. This can be seen also in the covariance matrices. If you see how the CLs, the angular power spectra for the angular density fluctations and the angular redshift fluctuations behave, you see that on smaller scales, non-linear evolution, non-gravitational linear evolution, non-linear physics couple the off-diagonal terms, couple different multiples in the small scales. But this is not the case for the angular redshift fluctuations. So we can say that actually angular redshift fluctuations are more linear or more Gaussian than angular density fluctuations. And well, this has some explanation, and it is the fact that I don't want to get deep here, but when you have this is showing for a given angular redshift fluctuation, so a given central redshift, we're picking up the densest pixel, having an overdensity of 11. Okay, so in this particular, this is from a simulation. In this particular, in real space, when we ignore the velocities, you have a bunch of galaxies at a given redshift of redshift 0.5, and it's giving this overdensity. And this is the weighting function for the angular density fluctuations. However, the angular redshift fluctuations are sensitive to the gradient under this Gaussian shell, to changes around this Gaussian shell. In real space, this happens to fall close to 0, so you have that angular redshift fluctuation is very small. And in redshift space, when you take into account peculiar velocities, the angular density fluctuation is still extremely nonlinear. It has an overdensity of 11 still. However, for the angular redshift fluctuations, the smearing in redshift space of the position of galaxies causes that the contribution under the kernel of the angular redshift fluctuation is very small, because things get blurred out. Nonlinear velocities blur the nonlinearity, and you end up something which is close to zero. So contrary to what happens with density fluctuations, redshift fluctuations in the nonlinear regime tend to go to zero because of the nonlinear blurring induced by nonlinear velocities. So this is the average of 300 simulations from the patching mocks for which resemble BOS data of year 12. And in particular, when we pick up the nonlinear scale of 60 megaparsecs, we find out that have like a 7% error, and that the recovery velocity is around it's around unity, which is the ratio over the fiducial model over the expectation for the lambda CDM, and these are for the biases, right? And this is on what we find as well is that for the angular redshift fluctuations, this is not biased, right? There's no impact of nonlinear physics, and actually the average for this choice of nonlinear scales, our very simple model with one single bias parameter, linear bias parameter, and one shot noise term, we find that we are able to recover the correct cosmology with the mocks, and we are able to recover a bias close to 2, which is what the BOS team is saying, that these galaxies are typically having a bias factor of close to 2. However, if we look at the angular density fluctuations, and these are the light symbols, the bias is more or less recovered well, typically systematically higher values, but because of nonlinear evolution, the recovery value of the amplitude of velocities falls too short. Because our simple linear model for the bias is not realistic enough to capture nonlinearities for the angular density fluctuations, for the 2D clustering. So we are low biased. For this reason, we decided, yes, because we wanted to stick to this simple model, we decided to ignore the angular density fluctuations, and that's what we did, and just look at the angular redshift fluctuations. Okay. And this is what we get in real data, right? So these are the simulations, and this is real data, okay? So we're measuring like a 10% above the fiducial expectation for the peculiar velocities, but still compatible because we have like 7% error. But the similarity between the simulations and the real data is striking. And this is the prediction from lambda CDM. This is the relative amplitude of the velocities over the expectation over the fiducial lambda CDM model from Planck. And things scattered tiny error bars at high redshift for the CMAS. At low redshift, we have only 2 points below the model. Maybe there's some slight hint here about nonlinear effects or something abnormal, but will have no significance, right? So as of today, even the low C part of the catalog, the low C refers to low redshift. These galaxies are harder to model because they are more affected by nonlinear evolution. But yet, on the scales we are looking with our simplistic model, this is still compatible with lambda CDM. No evidence, no signature of weird physics yet. So here we're showing, EF sigma 8, okay, which is this combination of parameters. If we compare this to, now, if you do 3D clustering, 3-dimensional clustering, anyway, so here is the comparison with other previous works. However, previous works work in 3 dimensions. They convert redshifts into distances. They use build boxes and then compute fast Fourier transforms transform in space. This means that they are not sensitive to EF sigma 8, but just to F sigma 8. But anyway, so I'm assuming that the E factor, this Hubble parameter, is the same, so that we can compare results. So our results are given in blue. This is our tomographic analysis from the angular redshift fluctuations, and the other ones are and the other ones are given by the different symbols. I want to remark here that in their case, they are going down to scales as small as 25 megaparsecs. And for that, they need to have a heavy modeling of the nonlinear physics. They need to have like 3 parameters for the bias. They need to model the nonlinear velocities with the fingers of God. They need to have a bunch of 3 parameters. In our case, our model is way simple. 1 single parameter for the linear bias, and that's it, okay? And yet, you say, okay, you have bigger error bars indeed, but we have more shells. And actually, if you try to constrain gravity, deviations from general relativity using this velocity amplitude, we're actually obtaining very competitive values, right? So, and it's funny enough, we are systematically, There were some discussion in the past whether general relativity was right, or whether this data, which is systematically below the lambda CDM prediction, which is given by the gray line, is suggesting some weird gravity. In our case, we are still compatible. Our gamma value is below. So gamma for equals 0.55 is the prediction for general relativity given by the green line. These are previous measurements, all of them systematically above. We are below, but yet compatible to this, right? So I think we're doing, so it really looks like, at least at this level of precision, that there is no evidence for deviations from general relativity. I switch gears now. I don't know, I'm going a bit slow maybe. Well, not too much. The thing is that this plot I just did yesterday, angular redshift fluctuations are correlated to the radial velocities. And this is good. So in practice, if you have redshift information on your galaxy samples, you can, from angular redshift fluctuation maps, you can build a map of the line of sight velocity under that particular redshift shell, right? Because we're doing tomography on every angular redshift fluctuation map is built upon a given central redshift and under a given Gaussian of a given width. So for every central redshift, you can build a map of the radial peculiar velocity under that Gaussian shell, redshift shell. And this is depicted in the right panel. Now, many of you are familiar with the kinematic or kinetic Sunyaev-Zeldovich effect, which is just related to the fact that moving electrons form some scatter of the CMB photons and induce some momentum to the CMB photon field. They do not distort the spectrum to first order, but they do change the intensity, and they do change the measured brightness temperature. So CMB photons coming from a cloud of electrons around a galaxy that is moving towards us will look slightly brighter or slightly hotter than average. And the opposite applies for a galaxy that is receding away from us. The electrons will tend to cool the radiation bath, the CMB radiation bath slightly, and this will cause a different, an opposite sign, brightness anisotropy. This is the kinetic Sunyaev-Zeldovich effect, which I try to explain here. Again, the same thing. This kinetic Sunyaev-Zeldovich effect is proportional to the line of sight velocity with a sign flipped, and also with the amount of electrons. Right? This has been measured in Planck data and in AC data. It has been measured in the last 10 years. It was first measured in 2012, if I recall correctly. Okay, so it's a recent effect. So the thing is that since the ARF, the angular redshift fluctuations, are providing a map of peculiar velocities, then the ARF maps should be anti-correlated to kinetic Sunyaev-Zeldovich fluctuations. So what did we do with our student, Hernandez Montero, now he's a postdoc, he's back now in Spain. We used Planck data, and we cross-correlated Planck full CMB map with maps of angular redshift fluctuations built upon spectroscopic surveys like SDSS main galaxy survey, which is going up to redshift 0.3, the quasars, and the 6DF galaxies. This is just a plot showing the covariance between the three set of surveys. So we conducted tomography. Each of these surveys is sampling different redshift ranges, and we picked up a set of central redshifts with a width of typically 150 megaparsecs. And we computed angular redshift fluctuations for each of these shells for all these three surveys. For every shell, we had like a map of angular redshift fluctuation that was cross-correlated to the CMB map from Planck. And this is the result of this cross-correlation. We actually find evidence for anti-correlation, as we would expect if the KSC signal is there in Planck maps. This is pretty much this, right? So this is for central redshift of 0.56, and then it depends how, there are technical details on how we extract the kinetic Sunyaev-Zeldovich effect. So the cross correlation is not done directly using our angular redshift fluctuation maps and the Planck maps. Planck maps are processed in the sense that we are trying to have an estimate of the kinetic Sunyaev-Zeldovich effect in the position of every quasar, of every galaxy, by applying aperture photometry with a given radius. So this particular plot is for a radius of 17 arc minutes. That meaning that we are somehow trying to capture the CMB anisotropy on the position of that particular galaxy within a radius of 17 Armenids. This is the perturphotometry. And from that, we can build a map of the kinetics and Universal effect coming from each of the galaxies. That is the map that is cross-correlated to the angular redshift fluctuations, and this is the map giving this type of anti-correlation, which is what we would expect theoretically. The thing is that we can change this aperture. I'm not sure if you can see well, but if you will repeat the analysis, this cross-correlation by increasing the amount of the radius around each galaxy on the CMB map, if we consider the CMB temperature in pixels that are falling within circles centered upon each galaxy, and the radius of these circles are increasing, then what we're doing is you are just sensitive to more and more gas around the galaxies, right? So if I go back here, say that the Planck experiment is looking to a galaxy, but the thing is that most of the kinetics and Universal effect is actually coming from electrons outside the galaxy, not only in the galaxy, but outside the galaxy. And the amount of electrons contributing to the kinetics and Universal effect increases if we increase the radius from the center of the galaxy. So if we increase the radius from the center of the galaxy, more and more electrons surrounding the galaxy will contribute to the kinetics and Universal effect. So by repeating this cross-correlation analysis of the angular redshift fluctuations with the kinetics and Universal maps that we build for different apertures, we're able to get these profiles, right? So here, every point here is our measurement of the number of electrons, which is just proportional to the amplitude of the kinetics and Universal effect that we measure for every different aperture. So here in the top axis, I'm not sure if you can see well, but this is the Armenids from the central galaxy. The maximum angular resolution of Planck is 5 Armenids, and then we extend up to almost 50 Armenids. And for every aperture, we compute the cross-correlation of our angular redshift fluctuation maps to the kinetics and Universal maps. The kinetics and Universal maps are different for every aperture. And this is what we get. This is at redshift, what? 0.09. This is for nearby galaxies. Then to 0.044, and we go up all the way to 0.73. Redshift 1.43. These are quasars already. Let me see. I just missed what is the central redshift around here. Sorry, I got lost here. The legend is not too good. But anyway, this is just for you to give you. So here it is. The effective redshift is 1.41 here. These are quasars at redshift 4, 4.62. 2. So we have at high redshift quasars and intermediate and low redshift galaxies. And for every aperture, we see some evidence, in some cases, clear evidence of kinetics and Universal signal. Here, here, here. And then we try to fit like a beta profile, a beta profile, or a different profile motivated by numerical hydrodynamical simulations, which is given by the orange line. But we see that for we can fit a gas profile around sources at redshifts as high as 4 or 4.03, 4.6, almost 5, right? So some cases we have little evidence for signal. Some other cases we have very strong evidence, right, depending on the density of sources that we have. But in many cases we have very strong evidence of gas, of diffuse gas around those sources, and these are very high significant kinetics and Universal detections. Actually, this is, if these plots here summarize our findings, and let me check out the time because I think I'm taking too much time. Oh, I'm fine, I'm doing fine. So here, this plot here on the top left is showing the fraction. We measure an amount of kinetics and Universal flux at every redshift, right? We have galaxies at low redshift, we have quasars at high redshift. These are the central redshifts on which we're applying this tomography, on which we're computing our angular redshift fluctuation maps, depending on whether we're using SDSS galaxies, 6DF galaxies for the nearby universe, or we're using SDSS quasars at the very high redshift end. Now, for every aperture, for the largest, and this is actually applies for the largest, for 25 Armenids aperture, we can compute what is the fraction of the signal that is supposedly coming from the galaxy itself or from the halo itself, because we have some estimate of the luminosity of the halo, of the flux of the halo, of the stellar mass. We can estimate what is the virial radius, the size of the halo, and how many electrons those halos host. And we find that the signal that we measure in every case is the signal that should be assignable to the halo is a fraction, and a small fraction of the signal that we measure. Fraction collapse here means that the fraction of the signal that is coming from the electrons inside the halos. And you see that for most of cases, it's just a few %. Most of the signal that we measure must necessarily be coming from outside the halos, must be necessarily coming from unbound gas. This is the so-called missing baryons, right? Actually, if we measure the overdensity within our aperture, for every aperture, we are effectively sampling like a cylinder, like a region around the galaxy. And we can measure the number of electrons. You can measure the amount from the kinematic Sunyaev-Feldovich flux that we measure through the cross-correlation. We can infer the gas overdensity. And you see that, typically there are some excursions of 200, which is like collapsed structures. But for most shells, we are at the level of 20 or 30, which is what you would expect, right? So we're finding a lot of gas outside here. Yeah, and here this is the fraction, and this is the fraction of the total baryons that we should have seen. If you say at redshift 0.5, we know that for that footprint and within that Gaussian shell, we should see a given amount. The total number of baryons is this one predicted by cosmology, predicted by our value of omega baryon. How many of them are we seeing? What fraction of those baryons are we finding with the kinetic Sunyaev-Feldovich analysis? Is given by this right panel here, right? And we're like, depends on the redshift shell. In some cases, we go above unity. Jonas has gone crazy. Our student went crazy finding out why we had this high excursion, but apparently there's nothing weird. This is just a statistical excursion. Note that we have a logarithmic scale here, but this is within 3 sigma. And the 2 points are not independent, right? Because there's some correlation between the two shells. But on average, we're finding like 50% of all baryons at every redshift shell, right? So this is, these two plots are the summary of our work. We're able to do actually a gas profile, measure a gas profile around quasars at high redshift, redshift 4, redshift 2, and galaxies at redshift 0.7 or so. And and we're able to count that this number of electrons, this amount of matter that we actually detecting is amount to about 50% of the total amount of baryons that should be present at those redshifts. Let me also summarize just to highlight the fact that this is the highest KSE, highest significance KSE detection. Our signal-to-noise ratio is about 11, right? Which is about twice as much as the latest detections that came along from the ACT team, from the Atacama Cosmology Telescope last month, I think, or 2 months ago. And this is only Planck data. We don't need high angular resolution for this, right? We need large scale coverage. Anyway, so this is the summary for the 2 works that have been published on the theory work, and now we'll keep working on this. So this is a paper that has been accepted recently too. It was led by Louis Legrand, who was a PhD student in Paris, in Orsay, and now he's in Switzerland. And we just simply, this is just a forecast for a spectroscopic surveys like Euclid or DESI, how much our uncertainties on the cosmological parameters shrink when you add angular redshift fluctuations on top of angular density fluctuations. So here you should look at the green lines and how they compare to the blue and the orange. The blue correspond to angular density fluctuations, the orange correspond to angular redshift fluctuations alone, and green corresponds to both of them combined. Here you see the errors on the cosmological parameters, and you see that you actually shrink the error region and you gain a lot of cosmological information. This is the summary. This is for DESI and this is for Euclid, but the 2 plots are pretty similar, right? So you see that you typically halve the errors when you combine, or even better than that, when you combine both observables. This is just theory. And this is assuming that, the thing is that since we're using angular quantities, and people from the Euclid community, they're always, and it makes sense. They get picky saying, yeah, but you should compare to the 3D power spectrum, or to the 3D angular to the 3D correlation function, which are the observables that people in LSS usually make. They're making use of. They're ones that they use in order to infer cosmology, right? So, and we're working on that right now. This is just to show that indeed there is added cosmological information on the ARF side when you combine them with the angular density fluctuations. Now, the full comparison of these 2 angular observables with the 3D observables, like the correlation function or the power spectrum, is ongoing as we speak, right? And also, we're doing many things now, and we're computing relativistic corrections to this. Now we're looking at how it applies to intensity mappings like SKI. So this morning I was, so this is, I'm doing this in collaboration with Stefano Camera in Torino. So we have written the first equations. So this is just the radiative transfer equation for intensity, for specific intensity, right? You have the absorption of the, due to the, have the tau dot. You have intrinsic anisotropies, they get blurred by the presence of, say you have like a transition, a resonant transition for H21 or for any other spectral line in the universe, right? So if you're looking at the CMB at that particular resonant frequency, then your intrinsic CMB anisotropies partially get blurred by the presence of, by this random scattering, this resonant scattering, although there is also a new a new Doppler term. If the scatterers have some peculiar motion with respect to the CMB, then they get some source of new anisotropy. And also you have the emissivity, right? You have some emission which might be collisionally induced, might be induced by the UV, by this field Volt-Hudson mechanism, whatever it is. But this is the radiative transfer equation. So what we're doing now is trying to apply this to angular redshift fluctuations. So in the language of intensity mapping, when you do not resolve the sources aren't resolved, and you're talking about average fluxes measured in a given region of the sky, then this is the expression that we have come up with for angular redshift fluctuations. So in standard language, the flux that you observe, that SKA we observe, for instance, with a given central Gaussian width, centering upon a given central frequency, which would correspond to a central redshift for a resonant transition, then you would be able to we're working on writing the angular redshift fluctuation for the language of intensity mapping, in summary, right? And you're just trying to make some progress on this. There's a bunch of other, other projects, right? So right now we're looking at the EBOS quasars and trying to measure FNL and other cosmological parameters from the angular redshift fluctuations. We're looking on the GR effects as well. We have some preliminary results on this. We're working on the extrapolation to H21, as I just mentioned. If I had a student, I'm curious about what is the sensitivity of angular redshift fluctuations on a BOS scale. We're trying to model the nonlinearities, also the neutrino masses, and cross-correlations with Ramanova surveys and so on. So there's a bunch of things that we're trying to work on, but our progress rate is rather slow, I'm afraid, because we're very few, and I just moved recently to Tenerife, and I've been kind of distracted. Hopefully, from now on, I will be able to work more efficiently. Anyway, feel free to ask as many questions as you want.
I think I have two questions. One is you measure the FB, the baryon fraction for your selected sample for Sloan and 60F and so on. And then how did you decouple the velocity from it and therefore be able to derive it?
We're assuming the lambda CDM cosmology, right? So once you fix your cosmological parameters, you have a numerical prediction for this, right? For the angular cross correlation between the kinetics Untitled and the angular redshift fluctuations. We fit for the amplitude, and the only free parameter of this amplitude is tau Thomson, right? Is the number of electrons. The dependence on the velocity is encoded in the assumed cosmological model, right? Which we fix to.
So basically, this is proportional to the. This is proportional to the velocity power spectrum.
That's right. Okay. The uncertainties from Planck on the velocities is what, 1%? If you believe lambda CDM, the uncertainties in F sigma 8, in EF sigma 8 is really tiny. Most of our uncertainties is actually coming from the measurements of from the amount of gas, right? So we're fixing this to lambda CDM expectations, to Planck expectations. We assume that velocities obey lambda CDM expectations, and then we infer.
Okay, I see. I see. And the other thing that how correlated is this data in between different L's?
So it depends on the particular. Do you mean multiple by multiple or shell by shell?
Yeah, I think both of them are correlated, right? So
the correlation in multiple space depends on the footprint, as you know, and depending on which survey, we're having bigger footprints or smaller footprints. So the smaller the footprint is, the larger the correlation is. But Jonas, I think he was running this on many simulations. He had like, using this COLA algorithm, he was building like many simulations and running his pipeline on these simulations with a realistic mask in every case. So he was able to compute covariance matrices, right? And so he was accounting for both the covariance in multiple space, and also you can see that he was also able to compute the covariance between neighboring shells. So here, for instance, for the quasar, a Sloan quasar, every entry in this box is a different redshift shell. So the diagonal is the autocorrelation of different redshift shells, but for some shells, there is some off-diagonal correlation, which is typically neighboring shells. In just a few cases, we have like some correlation 2 shells apart, right? Now, don't ask me why this is not symmetric here. This is our plot probably, right? But it should be symmetric. I would understand, from the diagonal. But but Jonas was our student, Jonas Chavez. He's very careful. He was computing the covariance between the different shells and finding that in most cases it was negligible, right? He did include though this covariance matrix when estimating the tau, the optical depth, right?
Okay, I see. Thanks. And last quick question is, for the work that you're doing for 21 centimeter, you apply that angular fluctuation to the 21 centimeter, then certainly you're going to search for the new hydrogen, right? So the purpose will be different from ionized gas. So then, what is the science behind it? What is your motivation? What is the science behind it?
In that case, it would be correlated, right? So so it would be. There should be some. First of all, just out of curiosity, like I didn't stress this much, but angular fluctuations are very robust against systematics, right? So provided that for angular fluctuation, for H21 or all these interferometric signs at 21 centimeters, well, actually you're looking at way lower frequencies because of the redshift, right? You have these systematics of the pickup, right? You're sensitive to just a wedge of modes because you have some contamination and so on. So I like to just write first cleanly how angular fluctuations map work in the context of intensity mapping, and then one step further would be to understand how systematics would impact the angular fluctuations. I have the intuition that maybe angular fluctuations will behave more robustly, will be more robust, or will be less impacted by those systematics. And also eventually, it'd be interesting also to see whether one could do, for instance, cross correlation between angular fluctuation from H21 maps during reionization and CMB maps. To see, I would expect naively to have some correlation, because at the end, the velocity of the matter is the same, regardless it is ionized or it is neutral. But there should be some non-trivial zero signal. I mean, there will be cross correlation between angular fluctuation maps and CMB maps at those high redshifts during reionization would not be zero, and I think they would probably encode a lot of interesting physics that nobody has yet explored. So I like to write with Stefano. We're just trying to write a first easy theory paper, trying to guess where things go. What are the main variables, how physics works, and probably we'll try to get deeper and deeper if we manage to make progress. The thing is that, as I said, we're moving very slowly, right? But this first paper I really wanted to finish this year with Stefano, and so I was making some little progress in the last week and so on. But eventually, first just some theory, then cross correlation with the CMB. I mean, we're interested in reionization, right? And H21 is probing the neutral part.
I understand, but if you push to that high redshift, then you certainly need optical tracer. But then that's going to be a challenge.
No. But that's the thing. I mean, I can do angular redshift fluctuations with H21 intensity maps too. Okay, so that was my last slide here. I probably, it's just very preliminary. But if I have say that this flux here stands for H21 flux, then I can, motivated by this definition of angular redshift fluctuations, I come up with this definition of angular redshift fluctations for an intensity mapping survey, like H21.
Sure. That I understand. Yeah, but what I mean, if you really push that to high redshift, like redshift above 6, the EOR, then what is your optical tracer? right? That's going to be a challenge.
But that's the thing about redshift 6. You have H21. Your tracer is above redshift 6. The medium starts to be neutral, right? It's completely neutral at redshift 10, and and then the ionizing bubbles start to increase below redshift 10, but still you have some signal that is telling you some physics about the reionization signals, about the reionization universe, and we want to compute what is this map. From the H21 during that end of reionization epoch, how it cross-correlates with the kinetic Swing-Eiffel-Deutsch effect from that region, from that epoch, right? And see whether this can be measured, whether these are prospects for measuring this cross-correlation, whether we can measure tau or not, these kind of things, right?
I see what you mean. Okay. No problem.
Thank you for good questions, Yinse.
Yeah, no problem. Yeah.
Hi, Carlos. Nice talk and long time.
Yeah, no time no see. How are you doing?
Yeah. Good. Yeah, no, I just wanted to know. So yeah, just I guess my questions focus mostly on the covariance. So the first covariance, when you add the ADF and ARF, do you take into account, the Fisher matrix forecast? Do you take into account the covariances between the fields, right?
Okay. Look, this is let's say we're looking at angular density fluctuations and angular redshift fluctuations in a shell that is centered upon redshift 0.5 and has a width of 0.01. Okay, so this is the redshift. This is the Gaussian shell. Okay, now for this particular pixel, we have a bunch of galaxies in real space that happen to sit all of them at redshift 0.5. This is probably a cluster, right? A cluster of galaxies. This is real space. There are no peculiar, no effects of peculiar velocities. What happens here? You can see this is the kernel for the angular density fluctuations, and this is the kernel for the angular redshift fluctuations. So they are clearly orthogonal, right? So you gain a lot of information because angular density fluctuations are decoupled from angular redshift fluctuations. They are intrinsically built to be orthogonal to each other, right? Okay. So when you compute the cross covariance between angular density fluctuations and angular redshift fluctuations, you get 0 because of the shape of the kernel.
Okay. Okay. Now that was one question. The second question was when you, I guess when you do the ARF, it looks like there's some, I don't know, I guess the bins are correlated, but it looks like there's some like oscillatory feature in your recovery. I'm not sure which figure, which page that figure is on. So it looks like there's some kind of, in the redshift direction, it looks like there's some oscillatory feature. Like one of those.
On real data? You mean here?
No. Yeah, on the real data. So I don't know, is that significant or is it highly correlated, these bins? Or?
No, the bins we checked, right? There's some slight correlation in the bins that we accounted for. Not much, though, right? Because this is 2 sigma. From here to here, this is 2 sigma, right? So look, I didn't mention this. We're using 3D for every central redshift. We're considering 3 different widths of the Gaussian shells: 0.01, 0.025, and 0.05. Mm-hmm. The thin shells are the ones that are sensitive to the velocities. Right. The thick shells are more sensitive to the bias, right? So the estimates on the velocities are not very much coupled. You see, they're not very much correlated. There's some correlation for neighboring points, but not too much, because of the distance between 2 shells is around 2 sigma, right? So there's some overlap that we accounted for. Now you're saying there's some trend. I'm not sure if you're referring to this. There's some trend to increase towards low redshift. Yes, there is some trend. It may be due to we don't see this in the mocks, right? The mocks behave well. Real data doesn't. Maybe there's some nonlinear character present in the data that has not been captured by the mocks. Maybe. Okay. We don't really know, right? The significance of this is weak, so we cannot really tell. Okay. But there's some trend to lift above the model at low redshift, indeed. Yeah, but we're working now on the nonlinear modeling of angular redshift fluctuations to go to smaller scales, let's say 30, and then shrink the error bars and see how things behave, right? But but so far this is what we know, right? Yeah, there's some hint there. This is kind of intriguing. I agree. Yeah.
All right, thank you.
Thanks to you.
Okay. Okay. Thanks. Thanks again, Carlos,
Thanks
for
to you.
the
Thanks a lot
talk.
for the invitation.
Yeah.
Right? It was nice talking to you.